Hello friends, in this video I'd like to solve the following problem from Concrete Mathematics textbook, problem 51 from the 4th chapter. We wish to prove Fermat's little theorem by expanding 1 plus 1 plus 1 and so on plus 1 to the power of p via the multinomial theorem. So, to make sure that we are on the same page, let's recall a few things. Fermat's little theorem can be written in this way, that if k is an integer and if p is a prime, then p divides k to the power of p minus k. It's the thing which we wish to prove. Exactly that. Next, the multinomial coefficients are generalization of binomial coefficients, and they are defined in the following way. N choose alpha 1, alpha 2, alpha k is defined to be n factorial over alpha 1 factorial, alpha 2 factorial, alpha k factorial in the denominator, where n, alpha 1, alpha 2, and so on are natural numbers, k is a positive integer, and crucially, these lower indices, alpha 1, alpha 2, and so on, they should sum up to n. And the multinomial theorem, which is again a generalization of the binomial theorem, says that a1 plus a2 plus and so on plus ak to the power of n can be written as the following sum. Don't be afraid. We are summing over all alpha 1, alpha 2, and so on, alpha k, over all natural indices whose sum is n. And we are summing n choose alpha 1, alpha 2, alpha k, and we are multiplying by a1 alpha 1, a2 to the power alpha 2, and so on, ak to the power alpha k. If you put k equals 2, you just get the binomial theorem. It's a vast generalization of the binomial theorem. And finally, think about if p is a prime. Think about when is this binomial coefficient, multinomial coefficient, p choose alpha 1, alpha 2, and so on, alpha k, when is it divisible by p? And so give this problem a try and I will see you in just a minute. Okay, so now I wish to consider a few cases separately. So I wish to consider case of p equals 2 separately. Well, if p equals 2, then we have the following. K squared minus k is just k times k minus 1, and it's obviously divisible by 2 because it's the product of two consecutive integers. Divisible by 2 because it is a product of two consecutive integers. No problem there. The funny things happen for all the primes. So let p be an odd prime number. Now we will need something more to prove our theorem. Okay, and now let p be prime other than 2, and moreover, and I will first concentrate on positive integers. Okay, so now let's take a look at the following number: 1 plus 1 plus 1 plus 1 to the power of p, and here we have k digits 1, k numbers 1. Okay, now, crucially, by the multinomial theorem, we know that this number can be written as sum over alpha 1, alpha 2, alpha k, which are natural numbers from 0, and whose sum equals p. and we are summing multinomial coefficients. P choose alpha 1, alpha 2, alpha k, and then the rest is 1 to the power alpha 1, 1 to the power alpha 2, and so on, 1 to the power alpha k. Very well. So really, the last part can be omitted. And now, very crucial observation. Notice that if alpha, let's say alpha I is between 1 and p minus 1, then our multinomial coefficient is divisible by p. Well, why is that? Well, we know that our multinomial coefficients, I should have mentioned it, but every multinomial coefficient is an integer. And now we know that p choose alpha 1, alpha 2, and so on, alpha k. It can be written as fraction p factorial, alpha 1 factorial, alpha 2 factorial, and so on, alpha k factorial, and we know that it's an integer. And now we can write it in the following way. Notice that p can be factored out, and we have p minus 1 factorial, alpha 1 factorial, alpha 2 factorial, alpha k factorial. And notice that p, factor of p, does not appear in any factorial in our denominator. So p does not appear as a factor of alpha 1 factorial, alpha 2 factorial, alpha k factorial. Why is that? Well, because our numbers, our factorials, are between 1 and p minus 1, and because p is a prime. So p cannot be divisible by any number less than p, except 1. Okay, so now we know that this entire number is an integer. So this thing right here is also an integer. Why is that? Well, it's because p is co-prime to every number in our denominator. So p does not change the fact that our entire thing is an integer. Okay, so now we know that our number is in fact a multiple of p, so p divides this number. So it's justified. And now, let's take our sum once again. Alpha k are natural numbers. Alpha 1 plus alpha 2 plus alpha k equals p, and we are summing p, choose alpha 1, alpha 2, alpha k. And now let's notice that this entire sum is congruent. We can omit every term with any index alpha 1, alpha 2. If any index alpha 1, alpha 2, alpha k, if any of them is between 1 and p minus 1, then we have something divisible by p, by our observation. So it's just congruent. We can just sum over all indices, which are either 0 or p. So we are not summing over natural numbers anymore, but over indices from 0 to p, 0 or p, let's say. Very well. And now, how many terms our sum does have? Well, it has exactly p terms, because we must choose one index to be p, and other must be zeros, so our sum is p. And in how many ways can we do it? Well, from p indices, we have to choose one to be, from our k indices, we must choose one to be equal p, and every other must be equal to 0. So there are exactly k choose one ways, which is exactly k. It's modulo p, of course. Okay, and let's go back. And also I should have written it, but this very sum which we are considering, it's just p to the power of k. So now we know that, k to the power of p, rather. So now we know that k to the power of p is congruent to k modulo p. So now we know that for every positive integer k, and for every prime number p which is not 2, k to the power of p congruent to k modulo p. And what about 0, and what about negative case? Well, if k equals 0, then obviously k to the power of p is just 0, it's just k. So our congruence does hold as well. And if k is a negative integer, then what happens? Well, k to the power of p is congruent to minus k minus k to the power of p, because p is odd. And now by our result, we know that minus k is positive, so it's congruent to minus k, so it's congruent to k modulo p. So in other words, our divisibility is true in every case whatsoever. I need some space, so I will put my sum higher. And now we know that implies, finally, that in fact for every integer k, and for every prime, for 2 also, because 2 was considered first, for every integer k, for every prime p, k to the power of p is congruent to k modulo p, i.e., in other words, p divides k to the power of p minus k. And that closes our proof. It's one way of showing Fermat little theorem by multinomial coefficients, by multinomial theorem. There are other ways, but it is what it is. It was suggested to do it this way by the authors of Concrete Mathematics textbook, and I have done it exactly. Very well. So thank you for watching, and I will see you next time. Goodbye.